Hey guys, this is my attempt to make up for the rough and probably confusing recitation today. So this is problem set 32. We didn't get time to talk about it because of me, but anyway, so I'm just going to go through it right now and answer all the questions and talk my way through it. Sorry the audio isn't as good as other videos. As I write, I think you're going to hear a lot of clicking. That's just because I don't have my headphones with me that record really well. So hopefully that's not a hindrance, and hopefully this is worthwhile. So I'm just going to start working through this and talking my way through it. So first law of thermodynamics in one sentence, that would be that the change in energy of the universe is equal to zero. Essentially, we can convert energy from one form to another, but we can't create or destroy it. That's the first law of thermodynamics. Two ways to increase the internal energy of a gas sample. Well, that comes from the equation delta E is equal to Q plus W. So we can either add heat or take heat out of a system, or we can do work on the system and take work out. Now, if we add heat, that's going to be positive. So then if we subtract heat, of course, it'll be negative. Work then is positive when the surroundings do the work on the system. Okay. Sorry, just make sure it's recording. We're recording. Good. The surroundings do work on the system. What does that look like? That looks like the volume decreases. In other words, the surroundings are compressing the gas. That's positive work. You're adding energy to the system when you do that. So then the other side of that is if the gas expands, then the gas is doing work, and that would be negative work. So then why is there a negative sign in front of the P delta V term? Well, that's because work equals negative P delta V, right? So then if we plug that in for work, we get this equation. Okay, and that's because we want the work to be positive when the volume decreases. So if the volume decreases, then delta V will be negative, but we want that to be a positive work, so we put the negative out front to cancel that out. It's just a sign convention. All right, and then part D, what's meant by a state function? State function is just a parameter or like a variable that is path independent, which means it doesn't matter how you get to that state, the value of that parameter at that state is the same. So, for example, volume is a state function. What does that mean? It means that if I have a gas that's 10 liters, it's 10 liters regardless of what it used to be. Okay, same thing with pressure. If I have a gas that's 2 atmospheres, it's 2 atmospheres regardless of what it used to be. That's a state function. So versus non-state functions, which have to do with change. So heat refers to energy being transferred into or out of a system. That's a change, and so Q is not a state function. And work also has to do with a change, in this case a change in volume, so work is not a state function. All right, so let's talk about these. Which of the following processes are exothermic or endothermic? In essence, what we're asking is Q, or my heat, positive or negative? So if it's exothermic, Q is negative. If it's endothermic, Q is positive. Okay, so that's what we're asking. So rubbing alcohol evaporates from the skin. This is endothermic. Why? I'm going from liquid to gas. And if I asked you to boil water, do you have to add heat or take it away? You'd all say add heat. So to evaporate alcohol, do you have to add heat or take it away? I have to add. And therefore, this is endo. Okay. I'm gonna, sorry, endo, because we're going from liquid to gas. All right. fog forms over San Francisco Bay. So kind of the background knowledge you had to have here is that when fog forms, it's water from the air that's condensing, and so you get these clouds of fog. So if I'm going from a vapor to a condensed liquid, that's going to be exothermic, because I'm going from gas down to a liquid. And if I asked you when I'm going from liquid to gas, do you have to add heat or take it away? You'd say add it, so then going from gas to liquid, it would release it, so it's exothermic. Okay, ice cubes solidifying in the freezer. Well, those are going from liquid to solid. That's going to release energy, because often it's easy to think about these if you reverse it. So if I'm going from a solid to a liquid, I'm trying to melt something, I have to add energy. So then to freeze it, it would be removing energy. Ice cubes in a frost-free freezer slowly lose mass. What does that mean? I think what that means is that the ice cubes are not melting. They're just sublimating. You're going straight from a gas to, so gas to, liquid, oh my goodness, solid to gas. Okay, they're losing mass because some of it's just sublimating, so I would have to add energy to do that, so that is endo. All right. Oh, I think I just realized this one is incorrect. Ice cubes solidify in the freezer would be exo. Okay. Let me check to make sure the rest of these are right too. So it's going to be endo, exo, exo, solid to gas to endo. Okay. Dew forms on a lawn overnight, so that's very similar to fog forming over San Francisco, except instead of going, it's pretty much the same thing. So we're going from gas to liquid, that's exo. And then molten aluminum solidifies, that's going from liquid to solid. That's going to release energy, so excellent. Cool. All right, hopefully I didn't make too many mistakes there. All right, if the reaction mixture to the right is a thermodynamic system and the pressure of the system is 1 atmosphere, what is the value of W? Well, what's going on here? It looks like we're just compressing this system, so the volume is changing. So I know that work is equal to negative P delta V. Well, delta V is, delta just means final minus initial, so this is just V final minus V initial. Okay, so now I have to calculate these two things. Fortunately, they give me an equation for volume, so I could say work equals negative P times pi r squared h final minus pi r squared h initial. I just put the final initial on the h because the radius is not changing and pi is not changing. So if I want to now solve for work, I would have work equals negative 1 atmosphere times pi. R is 15 centimeters squared. My height is 40 centimeters. Sorry, my final height is 27 centimeters. Minus pi, 15 centimeters squared. And my initial height is 40 centimeters. Okay. So if I plug that all into my calculator, what I get is pi times 15 squared times 27. First thing, I get 19085 centimeters cubed. I had a centimeter squared times a centimeter, that's centimeters cubed, minus pi times 15 squared times 40 minus 28274 centimeters cubed, which gives me which equals 9189 9.3 centimeters cubed atmospheres. Okay, well that's not a very useful unit of work. Usually for work, the units we want are liter atmospheres or joules. So I'm going to convert this into both. So 9189.3 centimeters cubed atmospheres. So then I could say, well, I know that there's 100 cubed centimeters cubed and 1 cubed meter cubed. So I use the length conversion of centimeters to meters, and then I just cube it all. Then I know that there's 1,000 liters in 1 meter cubed. Alternatively, you can just Google it. You can't Google it on a test. So I got 9.189 liter atmospheres. Right, so my meters canceled, my centimeters canceled, and I'm left with liter atmospheres. Okay, so that could be an acceptable answer. Okay, additionally, I could take my 9.189 liter atmospheres and use the conversion. I don't know if they give it to you here, no, if they give it to you later, that 1 liter atmosphere is 101.3 joules. And that would give me 930.9 joules. Okay, and the answer ends up being positive because this value is a negative number, and then the negative sign right there cancels it out. Okay. We're still good. Alright, so now we're going to calculate the PV work done in the following situations. That gives you the conversion from liter atmospheres to joules. So I'm going to do this. Sorry. Okay, so I know that work equals negative P delta V. So work equals my pressure, negative 1 atmosphere. Delta V will be 0.2 liters minus 0.03 liters equals negative 1 atmosphere times 0.17 liters, which gives me negative 0.17 liters liter atmospheres. Okay. Why is it negative? Well, it should be negative because the balloon is expanding, so that means that the system's doing work. And we said when the system does work, that should be a negative value. Okay, so that's in liter atmospheres. But then let's also put it in joules. So then I'd say negative 0.17 liter atmospheres. 1 liter atmosphere is 101.3 joules. Which gives me negative 17.22 joules. Didn't specify what it wants, so I'm just doing it in both. Okay, ooh, I'm going to run out of space. Let me shrink this. Okay, so now B. B, a researcher compresses a sample of gas, so it says compresses, so what should you be thinking? This answer should be positive, so let's do our math. From 25 liters to 5 liters by applying pressure of 150 atmospheres. Okay, so my work is negative P delta V, which is negative. The pressure is 150 atmospheres. The volume change is from 25 to 5, so it'll be 5 liters minus 25 liters. That's going to give me the answer of positive 3,000 liter atmospheres. So that's a fine answer. I could also say 1 liter atmosphere is 101.3 joules. That would give me an answer of 303,900 joules or 303.9 kilojoules. So either of these are correct. Let's do this last one. Your lungs expand to 750 milliliters against a pressure of 4 atmospheres as you take a breath from an oxygen tank while scuba diving. Okay, so work equals negative T delta V. The pressure is 4 atmospheres. Volume, they don't give us the volume, but they do tell us it expands 750 milliliters. Expanding is going to be a positive change because the final is bigger than the initial. So this will be 0.75 liters, which gives me negative 3 liter atmospheres. That's a fine answer. Or I could say 1 liter atmosphere is 101.3 liters, and get negative 303.9 joules. Okay, so that's how we can calculate work in this information. Should it be negative? Yes. Why? Because your lungs are expanding, so they're doing the work, so that's negative. All right, an expanding gas does 100. What is this problem? Expanding gas does 150 joules of work on its surroundings at a constant pressure of 101 atmospheres if the gas initially occupied 68 milliliters. What's the final volume of the gas? So in this case, we still are doing work equals negative P delta V, but in this case, we know the work. And the gas does the work, so what should the sign on that be? It should be negative. Negative 150 joules equals negative pressure, 1.01 atmospheres, and then we close the initial volume and we want the final volume. So the final minus 0.068. That's the liters. Okay, so can I just do math here? The answer is no, because this side of the equation is joules and this is liter atmospheres. So we got to change one of them. So I'm going to do is I'm going to say out of this negative 150 joules, let's just change that to liter atmospheres. So then negative 150 divided by 1, or 1.3, gives me negative 1.48 liter atmospheres. So I'm going to say negative 1.48 liter atmospheres equals negative 1.1 atmospheres times the final minus 0.068 liters. Okay, and now I can do the math. So I'm going to divide by the negative 1.01. And so that gives me 1.466 equals the final minus 0.068. And I get the final equals 1.534 liters. Is that right? Yes, it is. Okay, so we should get a number bigger than 0.68 because it says the gas is expanding. If you accidentally used the positive value, you'll get the wrong answer. Okay, so let's keep going. Figure on the left below shows a compression stroke of a diesel engine. So, right there. How does upward motion of the piston alter the internal energy of the gases trapped in the cylinder? So we know that the change in energy is based on heat and work. In this case, in the compression case, there's no heat involved. We're just compressing the gas particles. If I compress the gas particles, well, if I'm compressing, the surroundings is doing work on the system, so that's positive work. So work is positive. Well, if work is positive, the change in internal energy is positive. So you're increasing the energy of the system by compressing. Okay, so then the figure on the right shows the power strokes, now we're over here, of a diesel engine, as energy released by the rapid combustion of the air and the fuel vapor inside the cylinder pushes the cylinder downward. Okay, so this is going down because of the explosion. if the gases inside the cylinder are a thermodynamic system, how does the internal energy of the system change as a result of the combustion reaction and downward motion of the piston? So we want to talk about delta E, Q, and W. What are the signs? So, heat. Let's talk about heat. Well, I'm reacting, and this is burning, and combustion releases heat. So that means that Q must be negative, because heat is being released. Now, in addition, this piston is going down, so this gas is expanding, which means that the gas is doing work on the surroundings, and if the system is doing work, that's negative. And if Q and W are both negative, then delta E must be negative. Okay, so that makes sense, right? Because our goal in an engine is to take energy that's contained within the fuel and release that energy into the piston so the car will move. So it makes sense that delta E will be negative because energy is being released. State whether Q, W, and delta E for the system are positive or negative. Okay. So we're going to do this. A, B, C, D, E, Q, W, delta E. Okay. So for A, water freezes and expands. So if the water freezes, that means that heat's being released, because we want to melt water, it has to put heat in. So if water freezes, heat's being released, which means the Q will be negative. It expands. Something expands, it's doing work, so that's going to be negative. So delta E must be negative. Okay, letter B, student heats up an ice cube until it melts. So you're putting heat in, so that's positive. No volume change means there's no work, which means E must be positive. Okay, C, researcher compresses the gas sample and heats it up. So you compressed it. So that means you're doing work to it, and you heat it up. So you're adding heat to it, which means delta E must be positive. Again, delta E equals Q plus W. D, a researcher releases heat. So releases heat, that doesn't mean this must be negative, and produces several moles of gaseous product. Sorry, I should say research, a reaction. Several moles of gaseous product. If I'm creating moles, then we can assume that it's expanding if the pressure doesn't change, which means it's expanding, which means the system is doing work. It's going to be negative, which means delta E is going to be negative. Okay, last one, number 8. State whether Q and W are positive or negative and calculate delta E. Space, we're good. Okay, some gaseous reactions combine to form a liquid product, releasing 150 kilojoules of heat. So that means that Q equals negative 150 kilojoules because it's being released, and causing the surroundings to perform 75 kilojoules. So if the surroundings are doing it, it's positive. 75 kilojoules. So then delta E, I'm just going to write this up here, keep it over and over, Q plus W, delta E equals negative 150 plus 75. So that's going to give me negative 75 kilojoules of total change in energy. All right, 44 grams of dry ice absorbs 25 kilojoules of heat. So Q absorbs it, so it's positive. And the resulting CO2 gas does 2.5 kilojoules of heat. So the gas is doing the work. So it'll be negative, which means delta E equals 25 minus 2.5, which is going to give me 22.5 kilojoules. Part C, a sample of gas releases 2.9 kilojoules of heat. Releases it, so it's negative. Surroundings perform 830 joules. Well, the surroundings are doing it, so it's going to be positive. 830 joules. I'm going to change the kilojoules real quick. PV work on the gas, so delta E is going to be negative 2.9 plus 0.83, which is going to give me negative 2.07 kilojoules. The answer there. And then the last one, D, reaction releases 150 kilojoules of heat, so Q is negative 150. Release enough gaseous products to do 275 kilojoules of PV work while the reaction's doing the PV work. So that means that work is negative 175 kilojoules. My delta E is going to be negative 150 minus 275, which gives me negative 425. Okay, so that was the homework. Hopefully this explanation helped if you were hitting some walls and weren't able to work it out. So again, hopefully that helps, and we'll talk more about this on Thursday.